In this session, we will cover chapter 1 of the book, Elements of Programming. So section 1.1 to 1.3 are basically basic definitions of what are objects, what are values, and what is data. We are going to skip them. Next, we come to the concept of procedure. As we know, in any programming language, we have the concept of functions or procedures or methods. Function, method, procedure, everything is the same thing. All these terms mean the same thing. So, as per the book, we have four types of things associated with the procedure, like anything that can influence the behavior of procedure. So, first of all, what are procedures? Procedures are basically set or sequence of instructions to execute. So, a procedure have input and output. So let's say we have void function f which takes int x from int y, and let's say it simply prints x plus y. So we do std print line x plus y in string. So here we have x and y as input, and there is no output. Although std print line is an output, it is writing to a terminal, so we can say yes, it is also a part of output. It is modifying some state in the world. Next comes the concept of local state. Local state is basically all the set of variables that are defined locally. So let's say instead of printing x plus y, we first store the result in a variable z. Let's say int z equal to x plus y, and then we do std println. So here z will refer to the local state, a state or the set of variables which are created whenever the function is executed and which gets restored when the function is finished. Those comes under local state. Next comes the concept of global state. So global state is something that is shared with many functions and is persisted. Like we, like I should not go into the persistence here, but global state is something which is outside the function and the function can directly access it. So let's say we have a global static counter, which is int counter equal to 0. And what I simply do, I simply return instead of printing z, I simply return z plus counter. And I have integer here. Okay. So what I am returning? I am returning the sum of two input arguments plus the global counter. So let's say I set counter equal to 1 here, and I set, let's say, auto z1 equal to function application of 2 comma 3. Next I set counter equal to, let's say, 100, and I say auto z2 equal to function of 2 comma 3. Here we can see that we passed two input arguments 2 and 3 both times, like in line number 1 and in line number 2. We passed same arguments to the function, but the output for z1 will be equal to 5 and output for z2 will be equal to 105. So the output of function changed based on the global state. So we know what is a global state, basically global variables in simple programming language terms, or it can be singleton pattern or singleton object in, let's say, programming language of like Java or C#. Those will also come under global state. Next, we have the concept of on state. What is the state? So we have one type of variable that is left. We can have local static variables inside the function. So let's say I have int function f, which has static int counter equal to 5. And I always return counter plus plus. So now if I have auto z1 equal to f and auto z2 equal to f, I can see that z1 will be equal to 5 and z2 will be equal to 6. So this counter variable is not part of local state. Why? Because it is not destroyed after invocation of the function. It is persisted. It is not part of global state because this variable is only accessible inside the function, and it is not part of on state. Like it is part of on state. It is part of on state, and it is also definitely also not part of input output. Okay. Now we come to the regular types. So regular types are those types which behave like integer. Basically, we like the properties of integers that much. We specialized the name for them. Basically, the types which behave like integers are termed as regular types. So, what properties do these types have to satisfy? As per the book or as per the author, a type T is regular if it satisfies all these properties. First, it has a default constructor. it has a copy constructor and it has destructor. In C++, we know that an object comes into existence via call of a constructor and it goes out of memory or it gets destroyed whenever the destructor is called. Next, we have the assignment. So let's say we have T of object 1. We did something with object 1 and we do T of object 2 equal to object 1. So here we are calling, so in first line, we are calling default constructor. In second line, we are calling copy constructor. Nothing new here. And let's say we have another, we set object 1 equal to object 2 after some sequence of operations. So here, object 1 already existed before this line, right? Because we have defined object 1 here. What we are doing, we are simply trying to assign object 1 with the value of object 2. So if our type supports assignment operation, basically set the value of type T with other value of type T. Here we are doing assignment operation. But in case of T object 2 equal to object 1, we are creating object 2 and then initializing it with object 1. So that will call copy constructor. And if you are unaware of what are copy constructor and assignment, you should definitely refer to online C++ resources on what are their exact differences and how they are used and implemented. Next comes the concept of equality and total ordering. So in the previous session, we defined what is equality. What is equality? Equality is basically a Boolean function. Let's say bool operator double equal, which takes two objects, object 1 and object 2. And it simply returns Boolean value, which is either true or false. So if our type defines equality, basically we can check whether two objects of same type are equal or not. If the type does not define this equality operator, then we say that the type is not regular. Next comes the concept of total ordering, which is new here. So let's say we have a set S, and I will define what is the total ordering. We take any two elements. Let's say this is element A and this is element B. By total ordering, I mean that we can arrange all the elements of this set S on a number line. Basically, if A is not equal to B, then either A is less than B or A is greater than B. So let's say we have three elements x1, x2, and x3 from the same set. Instead of taking A and B, I am relabeling them as x1, x2, x3. So it is possible that x1 comes first, x3 comes first, and x2 comes first. X2 then. Like it is possible that x1 comes first, x3 later, and next x2. So what is the relation? We have x1 is less than x3, x1 is less than x2, x3 is less than x2. Okay, so if it is possible to arrange all the elements of the set in a sequence in a number line, then we say the set is total ordered. And counterexample will be, let's say, complex numbers. Why? Because what do we even mean by, let's say, 1 plus I and 3 plus 4I? Which is greater or which is less? Or let me take another example. Let's say I have I and I have minus I. On the graph, I exists on the positive y-axis and minus I exists on the minus y-axis. So which one is greater and which one is less? We don't know because we don't have total ordering or basically any type of ordering between two complex numbers. So the set of complex numbers don't satisfy total ordering. Okay, and underlying type we will cover it later in very late chapters. Now we have one more concept, which is well-formed object and partially formed object. So default constructor, as per the definition of the book, creates partially formed object. And what is the meaning of partially formed object? An object is partially formed if we can only perform assignment to it and we cannot destruct it. Let me give you an example first. So let's say I define int x. Under our definition, the default constructor of integer is called. But if we try to print the value of x, we know that it is undefined behavior or any garbage value can be printed on the screen. So we can't print it, or basically we can assign new values to it. X equal to 3 will make x equal to 3 from this point onwards, but its state is not such well defined between the copy constructor of integer and before it was actually assigned to some value. So we say that this object was in partially formed state. Okay, and let's say we take another example. We have the std string, type t as std string. So in std string case, we know that we can assign s1 equal to, let's say, abc of string. We can also destruct the string whenever, let's say, the scope of the string is finished. So do we say that s1 is partially formed object? The answer will be yes. Why? Because what is the requirement for the partially formed object? The only requirement is that assignment and destructors are defined, are well defined operations on that object. We don't see what are the other objects. So basically, std string is well formed object, yes, and every well formed object is a partially formed object. We have well formed object implies partially formed object. Okay, so basically, to recap, regular types satisfy four type of operation, like have four types of operations. One related to the lifetime, one related to assignment, or basically setting the new value, changing the values of existing object. Third is about arranging elements on a number line, not number line, on a line. Basically, we can arrange elements one after another or sort the elements. It is equivalent to sorting. And fourth, we have underline type, which we have not discussed yet. We will cover it very later in our sessions. Okay. So now let's come to regular procedures. So a regular procedure is some procedure where, let's say, it has object of type t1, object of type t2, object of type t3, up to object of type tn, and it returns an object of type tu. It returns an object of type u. So a function f is regular if replacing, let's say, we have t1, t2, up to tn, and x1, x2, up to xn, where type of t1 and x1 is t1, the type of t2 and x2 is t2, type of tn, xn is tn. So it says that if I call f of t1 up to tn, and I call f of x1, x2, xn, if their return value is same under the equality operation, we say that this function is regular. Okay, for same inputs, we are getting same output. There is nothing else here. So we covered regular procedure. Basically, the procedures, if for given inputs, we always get the equal outputs. Now coming to counter examples. So let's say we have address of operator, or basically reference operator. We can say auto address, which takes t of object by reference, and we simply return its address, return and of object. So let's say we have int x equal to 3 and int y equal to 3. Calling address on x and calling address on y will give us different outputs. Why? Because we are calling address of like we have x and y both have same value. So we have x equal to y. But address of x is not equal to address of y. Therefore, address function is not a regular procedure. Okay. Next, similarly, the book gives examples of global state and pseudo number generator. For our, let's say, discussion, we will not distinguish between regular and functional procedure, and we treat both of them as a functional procedure. Like I will make a distinction whenever the distinction is required, but from our, let's say, as a working definition, we say that a procedure is a functional procedure if for given set of inputs, it always returns same output, irrespective of how we call that function or procedure. So what is the benefit of these type of procedures? There are many benefits. First of all, they are very easy to test. Why? Because the output of these functions only depend on the inputs. It does not depend on any global state or let's say database connection or anything else. Second, they are very trivial to parallelize because if I call this function once and I call same function twice from let's say same thread or different threads, then we are sure that these functions do not share states. Basically, I have let's say thread T1, I have thread T2, and I have the same function f. If T1 calls f and T2 calls f, we are sure that there will be no data race, there will be no undefined behavior due to any data races. And if such property is applicable to the function, we say that function is pure function or regular function or functional procedure. Any definition will work for us. Okay. Next, we cover domain and definition space. Very easy things, similar to how we defined domain and codomain in our previous session in mathematics. So, what is domain and definition space? Let's say I give you a function which is int square int x, and it returns x star x. Basically, we are taking the square of this integer, input integer. So, what is the domain? Domain of square, domain of square is set of all integers, but definition space of square is set of all integers where we are talking about 32-bit signed 2's complement integers such that their square is representable in 32-bit unsigned 2's complement integer format. So basically, if I call square with let's say int max by 2, then we definitely this will overflow. But if I call square if with 3, we get 9. So basically 3 will be in the definition space, but int max by 2 is not in the definition space of square. Why? Because the output is not representable or square function will not give the correct answer for this input. Okay, but both are in the domain of the square function. Why? Because we have specified that the input type is integer. So we have domain and we have defined splitted it into two parts, one of definition space, one outside definition space. For definition space, we know that answer is correct or function is callable on these inputs. But for inputs that are outside the definition space, we don't know what will be the behavior of the function. Either the function can terminate and give garbage result, or function may go into infinite loop. We don't know. That's why we focus only on the definition space, where we know that for any input from the definition space, the output will be fixed and well defined. Okay. Similarly, we have codomain and result space. So for this simple square example, what will be my codomain? My codomain is the set of all integers, right? And for the result space is the set of all integers which are square of some number. Simple. And we have another concept of homogeneous functional procedure. So what is homogeneous functional procedure? It is simply a procedure with whose all input types are of same type. So let's say I am writing a function int add, which takes int x and int y. Without looking into definition, we can simply see that both the input types are of same type integer. So we say that add is a homogeneous functional procedure. But if I have something like this, where I have int power, float power, where I am first argument is float of x and second argument is the power, which is n. We are computing x to the power n here. We can see that first input is of type float and second input is of type integer. So this is not a homogeneous functional procedure. In homogeneous means same, and functional procedure we have defined earlier. Okay, this section is now completed. Now we come to the final section of this chapter. In the final section, we define something known as concepts. Giving some background, concepts are introduced in C++20 in the C++ standard, but they are work in progress from a very long time. Somewhere around, I remember 2003 or 2004, but not sure. Maybe even before that. So, what are concepts? Concepts are basically predicates. And what is predicate? Predicate is basically something whose output is a boolean. Output is boolean. We don't care about input. If some function returns boolean value, we say that function is a predicate. So concept is basically predicate on types. What does this mean? Let me give you one example. One example is in C++ standard std integral. It is a concept which takes, let's say, integer, and for integer it will return true. But if we supply float to it, it will return false. Why? Because float is not an integer type. Similarly, if we supply int star to it, it will return false. Why? Because int star is a pointer and pointer is not integer. Okay. So from syntactic perspective, anything that takes types as input instead of like values, we are not concerned about any particular value of the type. We are specifically concerned about the type itself. For this example, we never took the value of 1, 2, 3 or any integer. We directly took the input as type and we return true or false. So we say std integral is a concept here. Okay. Another concept is, as you can imagine, is pointer type, or basically is pointer. Maybe I don't know if this type is if this name exists in the standard library, but something similar must exist in standard library. Okay. Next, coming to three related concepts, which is type attribute, type functions, and type constructors. I will give one example of each. So let's say I have a type T. We have a function size of, which takes a type as input and returns how many bytes the type will take in the stack if it was allocated in the stack, obviously. For instance, size of char will be equal to 1. Size of float will be equal to 4. So what is it doing? Size of is a function which is taking a type as input and returning an integer in this specific example. Okay. Then we have type functions. What are type functions? These are functions which take type as input and returns type as output. For instance, let's say I have a type function which is, let's say, make pointer. It takes a type t as input and returns t star. Okay. Another example is std remove cv reference underscore t in the standard library. It takes, let's say, const int star or const int and it simply returns int to me. I can use it like this, using t equal to std remove cv ref t constant end, and it will return me int. So basically, t will be equivalent to integer after this point. Okay. So basically, type attributes are something which takes type t as input and returns some value. Type functions take a t as input and return some type u as output. And type constructor are related to type functions, but type constructor takes type as input and generates a new type. We have distinction here. Type functions takes something as input and generate a type which already exists. But type constructor takes type as input and generate an entirely new type. Okay. In C++ or Java, we have the concept of template for the type constructor. As an example, let's say we have std vector of t. If I supply integer to the vector, I get a new type vector of integers. If I supply, let's say, vector of char, so char is the input to the type constructor vector, and we get a vector of char, which is a new type. So this is the example of type constructor. Okay. Now coming to preconditions and post conditions. So let me give you an example. One example might be square root of x. So let's say I have float square root sqrt, which takes input as x and returns. I am not going to specific implementation, but let's say we have some implementation of square root function. Okay. So what is the domain? Domain is all the float, obviously. What is the codomain? Codomain is also float, as we have seen here. What is the definition space? Definition space is all the set of positive floats. Float such that they are greater than 0. Okay. What is the result space? Again, result space is the set of all floats which are greater than 0 and representable in IEEE 754 format, obviously. So what is the precondition here? Precondition is basically something that a function checks to ensure that the given set of inputs is in the definition space or not, in simple terms, basically. So if I have a check assert x is greater than equal to 0, this becomes a precondition. Why? Because if the function is called with x less than 0, or basically let's say I try to call with the square root of -1 or -3, it is not representable in the type float because it is outside the domain space, definition space. So any checks that are performed before executing the exact instruction of the function, those are preconditions. Similarly, what is the post condition? Post condition is basically a contract or a guarantee of some invariant. Basically, let's say I take the example of absolute function. I have int absolute and I take int x as input. And based on the condition, if I return some value, what will be the post condition of this? Post condition will be that if x is the output, or let's say alpha is the output, then alpha will be greater than equal to 0. This is the post condition. This is the guarantee from the implementer. Basically, the implementer of this function is giving the guarantee that irrespective of whatever be the input from the definition space, the output will always be greater than equal to 0. This is the post condition. And there comes a question. There comes a distinction basically. Why are we talking about preconditions and post conditions in the concepts? So basically, concepts are like preconditions or post conditions that are checked at compile time. But these preconditions which I am talking about, which checks whether given input is part of domain or the result space, like basically is part of definition space or result space, these are evaluated at runtime. We have two types of bifurcations, one running at compile time and one running at runtime. So concepts in modern C++ lingo, concepts are checked at compile time, while contracts, which are introduced in basically C++ 26, are checked at runtime. And they, along with the function declaration, forms the contract or basically API of how the function should behave. We will cover how to apply concepts in programming in later chapters. But I think you get the idea. What are preconditions and what are post conditions? And concepts are basically type of preconditions and post conditions which are checked at compile time. Why? Because they only take types as input and we can work with types without going into exact values at runtime. Simple, we can work with that. So yeah, this completes our discussion of chapter 1. And I hope you are able to now understand the book if you try and if you go and try to read the book on your own. Okay, so let's meet in the next session for chapter 2.